Ladies and gentlemen, welcome in the AIT Smart Test Laboratory. This is a place where we are usually testing equipment for power systems and low voltage and medium voltage distribution systems. In our lab, which is basically the power components are over there, we can realize low voltage networks up to 1 megawatt. So if you would like to have an overview, we can later discuss this chart. We have different sources. We can switch the grid in different configurations and have a number of feeder and renewable energy emulators there. And part of this lab is the research test stand, which is over here. And in this research test stand, we have basically the same functionality replicated in a smaller area and with less power. And one of the main features of this infrastructure is that we are able to combine simulation and real-world components. So in this infrastructure today, we would like to show you the cybersecurity measures that have been developed by the Sparks project. And in order to jump into this, I would like to welcome you here and introduce you to my colleagues. So there is Mario Faschang from AIT, Christian Seitel from AIT, BooJoong Kang from Queen's University, and David Umsonst from KTH in Stockholm. So first of all, I would like to say a few words about our system setup for the demonstration today. So as that has been shown by Henrik in the previous talk, we are looking at this scenario of a low voltage distribution grid with a number of PV systems connected to a transformer station. The transformer station is outside there, just has been set up there for our tests here. It's a smart secondary substation with a voltage controller inside. And from there we have a 61850 communication to the PV systems in the field. And the PV is actually over there, and some are simulated. So in this system, as Henrik has pointed out before, we have to take care about the voltage. So when the PV systems feed in power into the grid, the voltage rises. And in order to have a maximum potential of infeed, we are going to control the voltage using reactive power management. This setup can basically be split up in 3 domains. So there's a central domain, a communication domain, and the local domain of the local units. And today we would like to demonstrate measures here in the communication domain and in the field domain. So no central measures are included here today. So in order to get a short glimpse of how we have actually implemented this scenario, Mario will say a few words about this.
We have implemented the physical system that you have seen before here in the lab. It is a relatively complex setup consisting of a communication system simulator, which you can see at the bottom left. It simulates the IP network, where on the one hand the intrusion detection system is located at the bottom left. The controller that controls the PVs is located, and the resilient controller that we show as a countermeasure is located, and also of course the attacker is located in this IP network, in the simulated IP network, which is simulated on one of these machines here. On the bottom left, you can see a simulation of a distribution grid. So we have a low voltage distribution grid, whole distribution grid simulated with 4 PV inverters. And a very specific part of this setup is that one of these nodes is pulled out. Its voltage signal is the analog signal here at the back, that you can see it on the oscilloscope. This signal is amplified through this 30 kVA amplifier here on the top. And we feed the voltage signal here to this patch panel, where we have the real inverter connected. The real inverter is also connected to the communication simulator in order to receive the voltage set points and also in order to receive the attacked set points, which we'll demonstrate.
Right. So one last thing I have to explain you before we really can start with the demonstration, and that is how the local PV units actually do their reactive power control. You have seen the chart in the previous talk. We dive a little bit into detail. So this chart basically shows the voltage at the feeding point of the PV unit. And as this changes over time due to fluctuation of generation and load, the PV locally decides on the amount of reactive power fed to the grid or taken from the grid based on this curve here. It's a Q of U function, which is implemented in the inverters. And the Q of U function has 4 supporting points. And these supporting points can basically be configured either over a local interface, or in the scenario here, we assume that the substation out there is calculating optimal points and setting these up and on a regular basis. So that's everything you have to know. And now we can basically start with our demonstration. So let's get everything ready. The guys behind the machines. I would like to request you to put your mobile phones on silent mode, and please don't make any photos inside here today. Right. So, what are we going to do? We are fiddling around with this reactive power curve. So in the normal setting, as you have seen it here, it supports actually the voltage. So when the voltage goes higher, reactive power is taken from the grid to damp this effect, and vice versa. And what we are going to do in our first demonstration, we will just increase the gain of the curve. So we get rid of the dead zone and increase the gain to a very high level. And let's have a look what happens then. So how do we do that? Basically, we are doing a man-in-the-middle attack. And this is done by BooJoong. BooJoong has 2 hats today, so he's a good man and a bad man. First, he plays the bad man because he is the attacker and does the attack, but he has also implemented the intrusion detection system, so he can also play the good man. But now, put your bad hat on, and what are you going to do now, BooJoong?
Okay, thank you, Friederich. So, as you can see in this slide, so attacker always will be targeting any machines the attacker can attack. So once the attacker compromises one of the machines within any place in your system, the attacker can scan all the network to find out another target, to get into deeper and deeper. Finally, we'll arrive at the final target. In this, our demo, the PV inverter will be the last final target of our attackers. And as soon as the attacker arrives the final position, so the attacker may have time to investigate what device are they doing and what information they are sharing between the devices. And so there should be some time to know what they are doing. And then based on the knowledge, after they run something, then the attacker can do some sophisticated attacks to cause some damage on their devices, or to operate very less efficiently, or whatever the attacker wants. They can control the devices by the man-in-the-middle attack. So we are talking about how to damage the communication from the network. Then you can manipulate these commands and measurement reporting back to your control center or some security analytic centers. So that is what we are going to demonstrate it on attacker side.
Right, so let's do it then. So we will now switch the slides to seeing what's happening behind the curtains. So here we see the power grid simulator actually. So once again, you have an overview over the grid. We have as a scenario here, at the feeding point, the substation is there. And this node here is actually physically present here in the lab, and the rest is simulated. So that is the communication, the 61850 communication that is happening between the substation and the inverters in the simulation and also the real inverter. And here we see now the chart, the measurements from the real inverter, from this connection point. So we will see this chart a bit more often today, so let's get a bit organized here. So we see here absolute values. For example, you see here active power is 1 kilowatt that is fed in by the inverter into the grid. It's minus because it counts like a load, so negative load is a feeding. We have 230 volts, so everything is in a nice condition. And now we would like to start with the attack. So, guys, are you ready? Wonderful, inverter's ready. Okay, the attacker is now intercepting the communication, looking at the packets that are sent, looking at the update values, the supporting points of the reactive power curve, and writing new values. At the same time, it changes also the feedback to the control center or to the substation, so the operator won't notice any change in the commands. So this takes a while because we have to wait for some communication to happen, which is then intercepted. But yeah, so there you see the current settings here. And there we are, attack has happened, and the result is quite disastrous. So you see here, green is the reactive power, and blue is the voltage. So reactive power is actually swinging around, it's oscillating now, because we have this very high gain in the curve. You can also see on the top chart, this is basically the voltage against the reactive power, so the current system state is always oscillating between these 2 points on the curve. And we have a very significant impact on the voltage on the system, so this oscillation would actually be invisible in light bulbs, would also destroy maybe some sensible equipment like efficient light bulbs or also motor drives in the system. So this is a condition in which a grid operator really has to get active soon. And we just did this now in the whole low voltage grid, so there could be very many customers being involved. So you just saw here now the effect of the real inverter over there. In order to show what happens in the whole grid, we would have to simulate and wait this for quite a long while, so we prepared this chart for you. So basically, just as an optical impression, that is what happens over one day if we do this attack constantly on all the photovoltaic inverters in this low voltage grid. So lots of voltage variation, unwanted. You see the magnitudes here. It's quite significant. Right. So that was the first attack demonstration. So we will, in the end, have the possibility to discuss. If you have short understanding questions, I'm happy to answer them. If it's a discussion point, let's wait until the end, if that is fine for you, okay? Right. So now, what can we do against that? So the first part, now we will show you two of the countermeasures that have been developed in the Sparks project. And the first one is the resilient control approach, as it has been introduced by Henrik just before. So once again, the idea is basically we have a communication, a SCADA communication between the controller, in this case down out there in the substation, to the field inverters, and we add an additional component in the field, the resilient controller, which does basically, as Henrik put it, some thinking on the command that came in. Basically, it estimates the effects which would occur if it would take over the command, and then see from some kind of cost function if these effects are acceptable or not. And that's exactly what we are going to do. So David is the man who implemented the resilient controller. Maybe you can just say which rules the controller is executing today.
Sure.
Yeah, thank you, Friedrich. So as already mentioned in the talk by Henrik Sandberg, we have implemented 2 rules. One is for the voltage prediction. This basically approximates the whole grid from the perspective of the PV as a Thevenin equivalent, so just as an impedance and the voltage source. And with that we can get the power system law, as you can see in the slides. And then we look for the intersection between the Droop law and the power system law. And the intersection point gives us the new steady state voltage the system should converge to with this Droop law. But in the demonstration today, we focus on rule 2, which is the stability of the Droop law, and we basically check the gain of the Droop law and compare it with a critical gain where it could start to oscillate in the right conditions we just saw. And we will show later the distance between the actual gain and the critical gain. And if this distance is positive, then the system is okay, and if it's negative, the actual gain, K, is greater than the critical gain, and the resilient controller would not accept the set points.
So we will apply this second rule now to the system. That's what we are going to do. So once again, we're doing the same attack. We changed from the good shape of the curve to the high gain curve, doing this man-in-the-middle attack in the communication. And now we will demonstrate the result of the countermeasure. Are the guys ready? Yeah. Okay. Countermeasure is ready. We're getting back to the communication charts here. Okay, RC is now on. And we have seen here, this is still the old state of the oscillating inverter, and now at this point we have switched on the resilient controller, and it basically rejected the high gain command because it applied the rule number 2. So we see everything is fine now, oscillation has stopped, so the resilient controller was successful. So we can have, I think, a short look behind the curtains, how that internally looked, and maybe you can just say what we see there.
So basically you can see here that this small red line is 0, and before the attack happened and the resilient controller was active, this distance of the distance between the critical gain and the actual gain was above 0, so it was in a safe state. And when the attack happened, the resilient controller calculated the distance again, and you can see that it was a really high gain, so the distance went to minus 200, I think. Yeah, so that's why we reject it in this case, and yeah.
So, as we also have heard in the symposium, there of course are many, many different potential attacks, so we could basically show you all the day different versions of these attacks. We decided just to take one more go in this and play a bit more with this reactive power curve. So this time we are not increasing the gain, but we are going to flip the curve. So the result will be, before it was supporting the voltage, now it will worsen the situation. So if we have a high voltage at the connection point, then reactive power will also be fed in, which even increases the voltage at that point. So this is our attack demonstration number 2, and let's see what happens in our low voltage grid, which by the way is in Wunsiedel in Bavaria, because SWW is one of the partners in Sparks. And they are quite happy that we don't do it there, but we just do it here in the lab. So, are we ready for attack demonstration 2, guys? Starting the simulation. Inverter is ready. So once again, yeah, we are seeing here now the voltages. Again, in this case, we are attacking the PV inverters in the simulation, but here at the physical interface you can see this effect as well, because they all are in one virtual large grid, and the blue curve is the most important one here now. That's the voltage. For your orientation, the 0 line is here in the middle, so that's nominal value, and this would be plus 10% is the upper line, and we see now voltage is increasing. Did the attack already happen? No. Ready for the attack? So this is the normal operation. The sun is going up. This is why the voltage increased. But now the attacker is doing his job, flipping the curve. So it again intercepts the IC61850 communication, which can be seen here. We are waiting for another communication to happen, to change something. That's the man in the middle attack. So the man in the middle doesn't get active by himself. He waits for something to come across and then changes it. Okay, voltage is already here. It's rising. Made a big step now. The color intensity is also one of these analog things. I don't know why this changes. But anyway, we can still see it. Voltage is now at 8.9%, still rising. So 9.2%, 9.3%, 9.5%, 9.7%. And there we are. So this time it worked. So what happened here, basically the inverter has a protection mechanism. When the voltage gets too high, it will just disconnect from the grid. And that is what happened here. You see also the reactive and active power went to 0. So there is a disconnection from the grid. This has not much effect on the voltage here because this is just one. All the other systems are still running, but this one has disconnected and the others in the simulation will do so later. And so what basically is now the case, if we do this on a large scale, we lose quite a considerable amount of PV generation in the system. And in order to reactivate it, you have to go to every single inverter and reset it because it has activated this protection mode and it is disconnected. So that is the attack number 2 we would like to demonstrate. And now again, of course, the question, what can we do against that? Well, many different things. As we have explained the resilient controller before, the rule number 1 would have actually prohibited that as well, but now we would like to show you a more advanced countermeasure. So we are now introducing the intrusion detection system, which comes on top of the operation of the resilient controller. And BooJoong Kang will give us a small insight in what it does, but he still has to set up the system. Give him some seconds to do so. Just a second, no problem. So this is a domain-specific intrusion detection system for smart grids, and what does it do?
Do something good. Okay, so to protect your system, first thing you need to know how you design your networks. Then you can tell where you have to watch to protect, to see, to monitor your network system. So in this case, we have 2 important networks. So you will deploy these agents, actually one component of the intrusion detection system. So the agent will watch your traffic, any traffic you are sending between devices, in this case between controller and PV inverters. So then also obviously the agent will investigate some generic network detection mechanism. For example, whitelisting or signature detection for some malware to detect. And the agent will also transfer relevant information to the central machine. Here is that intrusion detection to have a higher level detection mechanism from some protocol violation or rule-based stateful analysis or some anomaly detections, or maybe you can use some machine learning as well. And also the IDS can report some information, some alert to the other countermeasure to have better information to investigate. In this case, we are sending alert to our resilient controller to have a better knowledge about that, then the RC can take better actions on some dangerous situations. So that is the idea is doing in this demo.
Right. So the intrusion detection is now activated in the system. And we will show we will show one example. Two things can be done basically with this setup of the intrusion detection system. We are even able to retrieve the original set points that have been set, because you can see the agents are looking at the communication at both ends, so they can detect changes in between. But what we do here is now the second example. So basically we inform the local resilient controller about the severity of the cyber attack. So that's the main thing we are doing here now. The attack is running, and let's have a look on the physical system here. So it's flat. Right, as it should be, exactly. So we have here a voltage. The inverter just in time went on again. This always takes some time, but that was quick this time. And we have a normal operation of the system. 900 watts are fed in. So everything is fine, of course, because we have activated the countermeasure. So let's have a look behind the curtain again, what happened here. And let's get a professional explanation of that.
Okay, thank you. So this is the visualization interface to our intrusion detection system. So we can visualize any network traffic information. So first two graph on the top, it shows the traffic volume at each network. So we had two agents at our system. So you can see two graphs showing how many traffic was there. And the second line on the left, there is a red bar graph showing attack levels from our system. So IDS was keep watching on our entire demo and saying we detected something. So the attack level is from now 1 to 3. Actually 0 to 3. Actually 0 is nothing happened, just normal situation. So you can see that there was no attack from the beginning, but you see the IDS tell there was some attacks with these different levels of dangerous. So one means there is some illegal connection or some man in the middle watching on your traffic. And second, the attack level 2 means some malicious set point or some additional some attacks have happened. And for the final attack levels, it tells you some manipulation or some injection, so some more drop has been made by the attacker. So you can define whatever you want from the IDS. The IDS is not just give you all the signature, all the rules, all the configuration. It provides you how to configure it to customize it for your systems. Then you can define any attack level or other information to share with your countermeasures. Then also the attacker can locate where was the attacker. It's based on the situation, but in this scenario, we are showing what was the machine keep doing the man-in-the-middle attack during our demo. And in the middle two tables show that IDS was able to detect some manipulation attack on the IC6150 communication channel. So the IDS could identify the original values and manipulated value. This information will be delivered to the resilient controller, and then the resilient controller can take the original value rather than just ignore the manipulated data. Then the system keep going on as the operator wish to operate. And the last one is or same information from the RC showing distance predicted voltage. So probably there must be something can explain by David about this later? Okay, yeah, he already explained it, right? That's it.
All right, thanks a lot. So, to conclude this demonstration, we have shown basically that also in today's implementation of distribution systems, there are a number of cyber attacks possible. I think this is also something we have seen in the whole symposium. And in the Sparks project, we have implemented a number of countermeasures. Two of them have been shown here. So one is a local measure, the resilient controller, which basically really works on local available information and estimates, which makes it quite resilient also against external influences. The other measure, as just explained, is the intrusion detection system. These two systems can operate in parallel to each other, so we also have then some kind of redundancy in security measures, but they can also cooperate in a way that the IDS is informing the local resilient controller about the current severity state, so the resilient controller can be more strict in rejecting commands, which it did in this case. So that was all from our side. Thank you very much for watching. And now we would have time for questions, 10 minutes.